Welcome back. In this part of the lecture, we'll be now talking about exponential decay. And so this is sort of the opposite of exponential growth. Instead of our population growing over time, our population will be shrinking over time. So notice that the formula for exponential decay is the same as the formula for exponential growth. The only difference is our decay constant, that instead of having a positive decay constant, which would make our graph be one that increases as time goes on, we have a negative value for k. Our decay constant is negative, which means we'll be decreasing in size over time. Of course, you know for an exponential function that has that horizontal asymptote of y is equal to 0, so our population will be tapering off and getting closer and closer to 0 as time goes on. One thing that we'll be talking about here will be, instead of doubling times, which makes sense if your population is growing, we'll instead be talking about half-lives. So a common place where exponential decay shows up would be in radioactive material, which is showing radioactive decay, which happens exponentially. For radioactive substances, they have what's called a half-life, which is an amount of time it takes for the amount of that substance that you originally started with to shrink in size by a half. So what happens normally, you start with a bunch of radioactive material and the individual atoms are decaying. So it might start out as a uranium atom, it will lose some of its material and become an atom of something else. So it has something where you'll have originally a certain amount of uranium or cobalt or some other radioactive substance, and that after a period of time, some of those atoms have degraded, have decayed, and become something else. And so we have less than the original amount. We're also going to talk about the application of carbon dating, which is the reason why this formula is as well loved and well known as it is. It's one of the things that can help us provide a approximate age for artifacts of formerly living beings or formerly living creatures. So here, for things that are made out of organic materials, we will be able to use exponential decay to calculate how old that item is. And we'll talk about that in an example coming up. So starting with this is true, Mercury 194. That is a chemical that has a half-life of 444 years. So that means that if you started out with that 300 grams of Mercury 194 and you did some time traveling and came back 444 years later and looked at the dish, there would be only 150 grams of Mercury 194 left. The other 150 grams, those would have degraded and decomposed into some other chemical. So the question that we have here is, number one, how many grams of mercury will remain after 5 years? Nice thing that we can do here is we can at least come up with a reasonable estimate based on what we know about this half-life. If it takes you 444 years for your population to decrease from 300 grams down to 150 grams, then after 5 years, very little should have left. In fact, I'm expecting my answer to be fairly close to the 300 that we started with. It takes many, many years, 444 of them, for me to lose half of my original amount. So after only 5 years, I should probably have most of my original amount still there. But of course, let's find out the exact values here. Let's start off with our formula. A of t is a0 e to the kt. And we know one thing already, which is that we're starting with 300 grams of mercury 194, which means that our original amount is 300. And one thing that we'll notice here is we have two things that are currently unknown, our decay constant and time. Now, we're interested in how much will remain after 5 years, so when time is 5. But before we can do that, we'll need to know what our decay constant is. So actually what I'm going to do now is take this and find out what is my decay constant. And I'll use the fact that we have a half-life of 444 years. I know that after 444 years, or when time is 444, that I should have half of the original amount. I should have 150 grams. So this is similar to, if you're thinking back to the previous video, the Streptococcus example, where we started off with using the doubling time to come up with the growth constant. Here we're starting off by using the half-life to come up with the decay constant. And there we go, I'm dividing both sides by 300. And then I'm going to rewrite this as a log by taking natural log of a half equals to 444k. So I now have that my growth constant k, or sorry, my decay constant k rather, should be natural log of a half divided by 444. Something that you could find if you used your calculator for a moment here, you could check to see that indeed this is a negative number. That, remember, for things where we're exhibiting exponential growth, our growth constant would be positive, and if we've got exponential decay, our decay constant should be negative. Of course, you don't have to use a calculator to figure that out, because one thing that we know is the graph of natural log has an x-intercept of 1, 0. You know that for values of x that are 1 or larger, the y value is positive, and for values of x that are less than 1, the y value is negative. So already I know, without needing to use my calculator, natural log of a half should be something that's negative. I'd have negative divided by 144. That should be something negative. So I feel confident that, yes, I'm on the right track here. I have a negative growth constant as I expected. So now I can rewrite my equation. A of t is equal to the initial amount, e to the k times t. And I just want to find out how many grams remain after 5 years. So putting in 5 for t. And then I can run that through my calculator and find that it's about 297.667. We're rounding to one decimal place, so 297.7. So in 5 years, 297.7 grams will remain. Just wanted to say a couple things about the calculator side of things here. So notice here, all of this, natural log of a half over 444 times 5, all of that is an exponent that's on that e, so e to the power of all of that. So if you were entering that in your calculator, you might enter that as 300 times e to the power of, and then left bracket, natural log of 1/2 divided by 444 multiplied by 5, right bracket. So by putting brackets around all this, then when I calculate it, e to the power of, it'll have all of that being the exponent. Or the other option, of course, is to do some sort of simplification. Here, if you're looking at this power that I have, this is natural log of a half over 444 times 5. That's the same thing as 5 over 444 times natural log of a half, which is the same thing as natural log of a half to that power. Natural log of 1/2 to the power of 5 over 444. So if you wanted to, you could actually simplify this. You could say, well, really what we have here is 300 e to the power of natural log of 1/2 to the power of 5 over 444. And e to the power of natural log, those are inverses of each other, so they would cancel each other out. You should be left with just that power, that 1/2 to the power of 5 over 444. So if you feel like doing this little extra simplification to make your calculator work a little easier, you can, but of course you don't have to. And as I kind of predicted at the beginning, I would have pretty close to the full amount because only 5 years have passed and it takes 444 years for half of the material to decay away. And that's exactly what we found. 297.7 grams will remain after those 5 years have passed. So the follow-up question, how many years will it take for only 10% of the original amount to remain? So the original amount was 300 grams. 10% of the original amount, 10% of those 300 grams would be 30 grams. So the question that we want to address is, how long does it take for us to only have 30 grams remaining? So A of t is equal to 30 is what we'd like to know. We'd like to find out what is t. Okay, so we can again think about what should be a reasonable answer, or my answer where I roughly expect it to be. If you're thinking about after 444 years, you'll have 150 grams. And then after another 444 years, you'll have half of that, only 75 grams. And then after another 444 years, you'll have half of that, which is about 37.5 grams, which is pretty close to the 30. So I'm guessing somewhere in the neighborhood of around 1,300, 1,400 roughly is what I'm expecting to get as an answer. So let's find out. Let's find out if my estimate is close to the actual answer. Remember, this business of what I'm doing these estimates for, this is just to see, does my answer make sense? Of course, I know based on how long it takes for the material to decay to half its original size, that my answer should be somewhere in the neighborhood of 1,300 years, 1,400 years, somewhere around there. So if I got an answer like 2 million years, or 1 year, or 17 years, that would make me think that I should check my work. But if I get an answer that's somewhere around 1,300, 1,400, 1,500 years, I should feel fairly happy with my answer and I can feel fairly confident. Okay, so again, we are looking at the final amount to be 30 grams, and we want to solve for t. So 30 grams is equal to 300 e to the natural log of a half over 444 times t. And I'm going to do the same thing I've done so far as before, which is to isolate my exponential function. So divide both sides by 300. 30 over 300 is the same thing as 1/10. And then I'll rewrite this as a natural log. So natural log of 1/10 is equal to natural log of a half over 444 times t, and then just solving for t, bringing up that 444 and dividing by that natural log of a half. And then I just need to run that through my calculator. And when I did that, I found that t is about 1,474.936. So rounded to one decimal place, 1474.9. So it will take 1,474.9 years for only 10% to remain. And again, that kind of makes sense. After 444 years, you'll have half. After another 444 years, you'll have half of that, which is 25% of the original amount. And after another 444 years, you'd have half of that, which is 12.5% of the original amount. So, not a big surprise. Around 1300-ish years, in this case, 1474.9. That's how many years it should take for only 10% of the original amount of Mercury to remain. Okay, so one little last example to do before we take a pause, which is a carbon dating example. So just to mention how this all works, and when you are a living being, and this is whether you're a living being that's a plant or an animal, any sort of a living being that takes in nutrients. So that is taking things in from the soil or eating other beings, so eating plants or eating animals. Any of those sorts of cases are cases where you're going to be bringing in radioactive carbon into your body. Regular carbon that exists on the planet, most of it, carbon-12, is not radioactive. However, there is a certain amount of carbon-14 present in the planet that is radioactive. So the idea is that if you are currently alive, and anybody who is currently alive, the percentage of the carbon in your body that's carbon-14 should remain a constant. As long as you're alive, as long as you're eating, as long as you're taking in nutrients. So whether we're talking about me, or whether we're talking about a rabbit, or whether we're talking about a tree, anything that's currently taking in nutrients will be taking in radioactive carbon. So the percentage of radioactive carbon should be the same in your body as it is in anybody else's body. Now, once you die and you stop taking in nutrients, then you stop taking in new carbon-14, and the old carbon-14, as always, is decaying because it's radioactive. And so that's the idea behind carbon dating. We know what percentage of the carbon in you should be radioactive if you were alive. And so if we look at, let's say, a bone that we find, or some organic material that we found buried in a field, we can see how much carbon-14 is in it currently, and how much is that compared to how much should be in it. And then we can just use the fact that carbon-14 has a fairly reasonable length for a half-life, 5,730 years, and we can use that half-life to figure out how old must that bone, or must that plant material or other organic material be. So here we found an animal bone in a cave, and we'd like to know how old is this bone. And so A of t, that is the amount of carbon-14 currently present in the bone, so t years after that animal has died. So the first thing that we want to know is, what is the decay constant? And this is similar to the example that we did in the previous video with the Streptococcus, where we don't know the original amount, and we don't really need to know the original amount. The fact that we know is that after 5,730 years, the amount of carbon-14 you have will be half of the original amount. And so we're going to use that idea to find out what is our growth constant, because we know that A of t is our original amount times e to the kt, and that when time is equal to 5,730, that the amount of carbon you'll have should be half of the original amount. And if I divide both sides of the equation by the original amount, whatever it is, I don't have to know what it is, I can solve and find that e to the 5,730k should be equal to a half. And that allows me to come up with my decay constant. Rewriting this as a logarithm, natural log of a half equals 5,730k, and then dividing by 5,730 to find that my decay constant, natural log of a half over 5,730. And now that I've got my decay constant, I can now answer the following question. So this bone, we've assessed it, and it looks like it still has 83% of the original amount of carbon-14. So that means what we currently have is 83% of the original amount. What we want to know is, what is T? T is how many years is it since the animal died? So that's what we want to know. What is T? How long has it taken for this bone to have lost 17% of the original amount of carbon-14? How long does it take for us to still have 83% of the original amount? So away we go. We know that we want to have 83% of the original amount. And we want to solve for t. So I'll start off with 83% of my original amount is original amount e to the decay constant times t. I'll divide both sides by original amount. And this is why we don't really need to know the original amount. We only need to know the percentage here. What proportion of the original amount do we still have? And then now I'll take this and rewrite it as usual, rewrite it as a logarithm. So I'll say then we have natural log of 0.83 is natural log of a half over 5,730 times t. And then now solving for t, 5,730 times natural log of 0.83 divided by natural log of a half. And then running that through my calculator, I get 1,540.32. Let's just double check that. We have 5,730 times natural log of 0.83 divided by natural log of a half. And that is 1,540.32. And so if we're giving our answer now rounded to 1 decimal place, then I'll say here that the animal died approximately 1,540.3 years ago.